Hey you folks, Quill18 here, and welcome to another episode of our Unity tutorial, codenamed Project SpaceCube, where we make our little spaceship-y kind of building game of awesome. Now, the last episode I promised something probably kind of dumb. I promised, hey, we're going to take a look at shaders in the next episode, i.e. this episode over here. Because last episode we added this little space dust effect, which works pretty well. We do have to, yes, fix the skybox. Actually, you know what? Hang on a sec. For now, short term, let's go into lighting and remove the skybox. We're just going to make it a solid, like just black or nearly black kind of color. That's going to be our sky instead of that. Oh wait, sorry, that's the ambient color. That's not what I'm looking for. I guess I just don't want a skybox, right? There we go. And the camera background, so if we go to the camera, where's the camera? Right over here. Doom. We're just going to set the background to a much darker sort of deeper color over there. Okay, so we're going to do that. I guess I can close this. And now we've gotten rid of the terrible sort of skybox, and we have our space dust. Excellent. We still need to add proper space stuff later on, but we've got that. It's looking cool. Now, the problem is we've got these dust motes that give us a sense of motion, which is particularly important when we're attached to the object, because the problem was, when we go into flight mode, our camera is locked to the cube over here, and therefore we didn't get, like, here we have the relative sense of motion with the cube, but when the ship is moving, we weren't. So the dust is there, but it's got this pop-in effect that's going on, right? I'm pretty happy with the distance. Maybe we want it further, maybe we don't, I don't know. But even no matter what we do to tune the distance, at some point the dust will go from not being there to being there because of the way we've implemented the system. And it would be much better if it sort of faded in from a distance. And so the easiest way for us to do that is to implement a shader. It's very, very fast. Also, one of the things that I mentioned, I think briefly in the last episode, was Unity can actually render a crap ton of objects simultaneously with very little overhead, as long as they all have the same material. And there's various types of batching techniques. Not going to go into it, but one way that you could have the transparencies, you could have a script on each one of these dust motes that, or I suppose we don't need a script on each one. Our dust field could have a script which goes through each one of these, and based on the distance from the camera, could go and tweak the material on there to give it a transparency. Well, yes and no. Our current material doesn't actually give us the ability to tune, to set a transparency, but you could do something. You could use a different material which had that ability, and then you could tune it on a dust mote by dust mote basis, but that would mean each dust mote had its own material, and as a result, you would actually lose a lot of really good batching opportunities that would improve your performance. So, it's much better if you don't mess with the materials on an individual dust mote basis, but instead, in this case, make the shader, make the material itself a lot smarter. So a material in Unity, it's very important to note, a material in Unity is kind of nothing. What a material is simply a front end to interact with a shader. Basically, when you have a material, you do pick a shader. Most of your materials will use the standard material, but sometimes you will use something different. And the material just gives you basically the inspector UI to interact with the shader itself. But the shader does all the work of using the linked texture and using the past mesh information to actually make the information visible on screen. So what we're going to want to do to make the space dust become transparent the further away it is from the camera, we're going to have to tune this shader. Now, it is worth noting that while you can create a new shader from scratch, I can go and say create shader, if I can see it, but I am blind. There, shader over here. And you do get to choose a default one. So for example, we're using an unlit one. So I guess we'd be like, okay, I'll make another unlit shader. That's fine, which will have some sort of name over here. And you can double click on it and it'll open up in MonoDevelop. And that's fine. You can take that route. That is totally okay. I'm just going to keep this one here. You can do that. The problem with this is that sometimes, then we're going to have to do a lot of work to make this function the way we want. In particular, we have to make sure that we're on the right render type, the right render queue. We have certain things with alpha blending set up to get everything working right with transparencies and so on and so forth. Usually, you don't want to just create a generic shader. Usually, what you're going to want to do instead, so let me actually just delete this one. Instead, what you're going to want to do is start with an existing shader. Like, for example, with our space dust, we're mostly happy with the unlit/transparent shader. It does does almost everything we want. We just need a little bit of tweaking. So it'd be great if we could simply edit this one. Now, unfortunately, all the shaders that are in here in Unity are already, they're pre-compiled and pre-set up for you. You can't go and access the base shader or make tweaks to it, not from the built-in UI. Instead, you gotta sneeze. Excuse me. Oh, god damn. I'm sneezing like at least, I don't know, 10% of my videos. It's crazy. Instead, what you have to do is you have to go to the Unity website to download their archive stuff. If you just search for Unity Download Archive, or, because I can never remember that name, I just type in Unity Shader Download, will bring you to this page. If you just Google Unity Shader Download, you'll end up here. And this has got every version of Unity that's out there. In case you ever have a project that requires you to have a specific version or something like that, there you go. Not only that, but, so normally the pull-down menu over here would let you download various, installers and whatever. One of the things you've got the ability to do is to download the built-in shaders, the code for all the built-in shaders, which normally you can't access. So that's what you do. You would go and click download built-in shaders. It would download a zip file, and when you unzip that file, you get this. You get this kind of folder set up over here. So this is the unzipped version of those shaders. And if you go into default resources, nope. Default resources extra, that's the one that we want over here. Here is all of our shaders. And in particular, we were looking at the unlit shader over here and the transparent unlit one, which is this one here, unlit-alpha. Alpha blending is that sort of transparency aspect. So there is our shader. So what we want to do is we want to click on that, and that opens in my text editor here. Hang on. So yeah, so it just opened up in my text editor over here, which is fine. I'm just going to copy all that. Just select it all, copied that. And then what I'm going to do is I'm going to go back into Unity, and I stupidly got rid of that shader. Let's go and create shader. It actually doesn't matter what I use as my default shader over here. I'm just creating a new dummy shader file. Actually, what I could have done is actually grabbed this file over here, copied the file, and put it into my asset folder. That actually might have made it a little bit easier, but that's okay. So we're going to create this new shader. I'm going to call it something like Space Dust Shader, like that. Double click on it to open it up inside of MonoDevelop. I'm going to say just keep the Unix ending, it's fine. Open it up in MonoDevelop, and then what I'm going to do is I'm going to paste in the copied. So this is the shader that we downloaded from Unity. This is the exact unlit/transparent shader that we were using before, okay? Exactly the same as before. And if we give it a different name, let's go and call it something like custom/space dust, okay? So we've given a name. I save this. I go back to Unity. It compiles the shader. We've got it here. I'm going to move it. I think I'm going to move it into the materials folder. I think that makes a lot of sense. And on our material space dust over here, instead of being unlit/transparent, we're going to go, you see there's now a custom folder, space dust. So this here, this organization is based entirely on what we type in. Why did you do that? Why did you go away? That was odd. Oh, probably because it had the old one open. I moved it. Right, you got confused. It's literally here. Now, it's worth noting that this area over here is basically like the Unity material stuff. The actual shader stuff is happening inside of here. This is the CG program where you type your actual shader code. Everything else is sort of Unity glue stuff. But this part here determines the name. This part here determines what properties show up in the inspector. So this main texture over here called base RGB trans A. It's like, what kind of name is that? But if we look at our material space dust over here, you can see base RGB trans A. That's it. I'm just going to call this one. Let's rename it something nice, like the, I don't know, main texture. Sounds like a good name. So if we do that, hey, it's called main texture over here. Okay, that's great. So we have a fully functional shader. We have told the material space dust to use this custom space dust shader, and that's good. Now if we hit play, we're exactly where we were before. Right? Our space dust looks the same as the old space dust, but it still pops in and out. So what we want to do now is we want to have this fall off at a distance. So what we're going to want to do is figure out some way to do that. Basically, we need to know how far away is this mote of dust from the camera. Actually, we don't actually care about the distance of the mote of dust itself. What we care about is the pixels. Well, I mean, there's multiple ways of doing it, I suppose. trying to figure out the best way to explain this. I guess we're gonna be looking at each vertex. So in our little 3D object that makes up our space dust, we're gonna say, listen, for these vertices, how far are they from the camera itself? And it's actually really easy to figure that out. So we haven't looked at the shader stuff too much. This is not going to be an in-depth shader tutorial. I've actually done a little bit more shader work. But let's go through the rest of these lines over here. So this is the interface for Unity, what the shader is called. These are the properties that show up in the inspector. We're actually going to add another property here later on. Then we get the sub-shader information. You can actually have like multiple sort of shaders and passes and things. Anyway, it's fine. These tags are important to tell the system that this is part of the transparency layer. And in particular, what it's going to do, because of this Q equals transparent, this actually gets rendered last. It's quite interesting. Unity will render all the other objects first, and then render the transparent object on top of that. And the reason it does that is because that way, the stuff that's behind our transparent particle will still be visible in some amount, because we're rendering the transparent stuff afterwards. But because of Z indexing, if the dust particle is behind something, then it won't get rendered. Okay, so even though it's being rendered last, it'll only get rendered if the individual pixels are visible. We don't write to the Z buffer, which isn't really important one way or another here. Well, sort of, kind of. Let's just ignore that. The Z buffer itself, okay, maybe I won't ignore it. The Z buffer itself is basically like another image. You know, ultimately, you're outputting a bitmap, right? You're outputting some graphics to the screen, a single image. Well, you can also, that array, you know, your 1920 by 1080, whatever your resolution is, that array, you've got another one which simply includes information of the pixel here is this far away from the camera at this point. And that way it makes sure that when you're rendering stuff that is rendered later but is actually behind something doesn't overwrite whatever's in the front. If none of your shaders had any Z writing turned on, you would constantly be seeing stuff like behind walls and stuff like that. It would be weird. In any case, with our transparency, we actually don't, we're writing it last, so it's not as important with the Z writing, and actually you save a little bit, it's optimized a little bit if we don't write to the Z buffer, but also I think with the way the transparencies work, you actually do want to be able to write behind objects. Anyway, I'm sort of going off on a tangent here, and I apologize. This line here is quite important. This actually tells us how we're blending information to the screen. There's actually a bunch of different ways that you can blend your data to the screen, but this is simply, we're going to be using the alpha information sort of directly here, 1 minus source alpha. Excellent, fine. Okay, let's go into our actual program here. We're going to say that we have a vertex part of the shader. We also have a fragment part of the shader. This vertex part runs on every vertice in the 3D model sent to us. Fragment is, I don't know why it's called fragment, actually. I'm quite curious. I think it probably has to do with how the video card like parsed out the job. But basically, the fragment function runs once for every pixel that gets rendered. So this could be called the pixel part, right? So this runs once for every vertex in a 3D model. This one runs once for every pixel on the screen, effectively. Every pixel on the screen that, you know, gets involved in this particular object. This is just version stuff and something about fog, we're fine. This includes some basic functions that Unity provides for us that actually we're going to use one of those, which is really handy. And over here we've got two structures that we define. You can add more information here. It's a little bit black magic-y, so we're not going to mess with this in this particular scenario. Or am I lying to you? I am actually lying to you. We are going to add something to this. Aha! But this represents the information that's going to be passed from the object into us. This is actually going to be passed into our vertex shader, and this is the structure that the vertex shader is going to fill out and then pass to the fragment shader later on. So we will look at that a little bit. Here we've got some variables to hold our main texture, and actually, what is this for in this particular code? Does it get used for something? Find? No, it's not getting used for anything. That's interesting. It's just got a, this float 4, this is basically an array of 4 floats. So the default here is defining an array of 4 floats that doesn't get used for anything. Why is that? Is it this part of the information? It might be. How interesting. No, because no, it's not. Huh. Well, let's move on. All right, here's the actual functions that do work. This is the vertex part of our shader. This is our vertex function. Again, this will run once for every vertex in our mesh. What it does is it takes in this app data, which tells us about the vertex's position as well as the texture coordinate of that particular vertex. It's used for some UV stuff, which is going to factor into how we actually paint our texture onto our box. You may remember from last video or the video before where we went to the Blender and we did some UV work. Well, that's what's going to factor into some of these things. Anyway, so our function here, we define a new instance of this v2f. This is the vert2 fragment sort of structure over here. We define a new one called O for output. Fine. I like more verbose stuff, but I suppose it's totally okay. And we, in this this output structure, we need to know what the correct final position of the vertex is. So unity object to clip position. So this is a function that is defined in here that just massages this vertex into another vertex, just making sure to do all the transformations for viewports and things like that correctly. And the output also needs to know some texture coordinate information, which we get from the input vectors texture and the main texture over here. So we do a little bit of manipulation here, and then we get some information. So we're not going to mess with those directly. That's not what we're interested in. There's also this unity function for fog, which we're going to leave alone. Not that we're using fog, but it's there. So what are we actually interested in? We are interested in answering this question. This vertex, how far away from the camera is it? It's an excellent question. Now, that's actually one that's relatively easy to answer. You can actually do you can do the math sort of yourself, but there is a very handy-dandy function to do that for us. There's an object or a function that Unity provides called obj_space_view_dir. This is a vector. This is basically just literally the camera's position minus the object's position, or potentially the other way around, the object's position minus the camera's position, which is a vector that is literally the distance between the two, right? The offset. It's called dir as in it describes the direction from one to the other, but it's important to note that this is not normalized. It's not a unit vector, which would, sort of be a more accurate description of maybe your standard direction. It is the true, just like, difference between the two positions. So what's nice about this, so if we go, and we're just feeding in our input vertex. So our input vertex over here, we're just feeding this into a function, and this is going to return a vertex that is the difference between the camera's position and this vertex's position. Well, if we use the length of this vertex, then this is the distance between us and the camera. Now, in a shader, you really want to be as optimized as possible. So normally I would do something like this, right? This is the distance. Okay, but you really want to cut down on overhead in a shader, because shaders run, in a sense, in a very real sense, it runs once for every pixel on your screen. The truth is somewhat more and less of that, depending on your scene construction. But it can run a lot of times, and it has to run every single frame. Now, your video card is really, really, really good at running a lot of these tiny functions very quickly. And part of the reason for that is your video card actually has like a ton of CPUs, depending on exactly what your video card model is and different things like that. It could have like 1,000 CPUs, if not more, actually, all running simultaneously. So you're actually running multiple copies of these functions simultaneously, very, very, very quickly, very high clock cycle internal to your video card. But it has very microscopic amount of memory. As such, you need these shaders to be as small as possible. There's actually a very distinct limit. It's very easy to actually hit the size limit on a shader where it literally can't fit in there and you'll get a warning. So you do have to make sure not to overinflate your shader code, but more importantly, the smaller it is, the better it will be, because it'll be more optimized for copying things in and out of memory on your video card. So we're going to avoid making any variables we don't need. So if we want to do a fade here, so this is how far away it is from the camera. So let's assume currently, what's our dust cloud fall off here? Dust cloud. Where's it? Dust field over here. Our cloud radius is 25. So right now we're making it so that our dust particles are never more than 25 units away from the camera. So right now let's hard code that in and say, okay, so 25. So what is the distance from the camera? So if we did something like this distance divided by 25, okay, what we would get is a number where when it's at the maximum distance away that our particles will ever be, which is 25, right? This could be as big as 25. So 25 divided by 25 would be 1. If it's right on top of our camera, this would be 0. So 0 divided by 25 is 0. So we're ending up theoretically with a number between 0 and 1. Right now, depending on how things work out exactly, you might get it slightly over 1. But, you know, for our sake, let's assume this is going to be correctly between a number between 0 and 1. But it's important to note that the further away this is, when it's at maximum distance, this equation, right? This equation, if we wrap the whole thing in parentheses, this equation will return 1 when it's at further distance. And an alpha of 1 means fully visible, and an alpha of 0 means fully transparent. So we want the inverse of this. So we want to go 1 minus this amount. So now, when it's at its maximum distance, this whole thing will be equal to 0. So that's what we want. Now, what we need, so this is some float, this is the correct alpha, is going to be this. All right? But what do we do with this value? We need to communicate this information to the fragment shader. The vertex just manipulates vertices. The fragment shader is what actually determines the color of the pixel that goes on screen, and specifically this. So this is color, fixed 4. So the fixed 4, so the 4 part is basically, this is shorthand for an array of size 4, is what this is. It's very optimized for this. Thank you, October patrons. Those are the people who pledged in October and who are supporting these videos from November through to early December, and especially these Mic Check supporters. We've got Yukofin, Adam Conway, Drazian, Jan Torivel, Adjective, Michael McClintock, Aaron Toyson, Craig Mortel, Stephen Wendell, Julien Auger-Lafont, Marius Fielvold, Speedy Savant, Valiant Cake Fiend, Wes Oldenboiving, Jason Yanity, Kale the Quick, Neil Blakey Milner, and absolutely everyone who watches, shares, favorites, and subscribes to these videos. Thank you very, very much.